In this lecture, I am going to talk about mean squared value of the output process. So, you have an LTI system whose impulse response is h of t, and the input is a random process x of t. The output is a random process y of t. Now, we wanted to know what is the mean squared value of this process. We know that the mean value is nothing but expected value of a random process or random variable. So you take expected value of y of t, then this is the mean value of the output, right? That's what we said. Now you take the squared value, like you take y of t and square it, you will get y squared. Now for this y squared, take expectation. That means expected value of y squared of t. So this is called a mean squared value of output process. Sometimes people use a square instead of squared, so the d will not come, only mean square. So either way you can call it. That's it. And we know that capital Y of t is equal to integral of x of t minus lambda times h of lambda times d lambda. Now what is y square of lambda? Just square of this, square of the right hand side, square it. Integral of x of t minus lambda h of lambda d lambda, square it. So, and then take expectation on both sides. Sorry. Integral you can write like this. Okay. By the way, this single integral I can write as, this also you can say expected value of y of t times y of t. Therefore, x of t minus lambda times h of lambda d lambda, then integral of x of t minus lambda, and the limit is minus infinity to plus infinity. You can write like this. Therefore, to find the mean squared value of the output, we must be able to calculate product of two integrals. This is one integral and this is the second integral. So therefore, product of two integrals. So to find the mean squared value of the output, we must be able to calculate the product of two integrals. However, such a product, this two product may always be written as an iterated double integral if the variables of integration are kept distinct. Okay. This double integral becomes, product of two integral becomes double integral like this, provided that if you are using variables of integration which are distinct. Okay, one for one integration use one random one variable of one variable, and for another integral use another variable. Both are from minus infinity to plus infinity. Now x of t minus lambda 1 h of lambda 1 times x of t minus lambda 2 h of lambda 2 times d lambda 1 d lambda 2. You can write like this, both are equal, valid expression. Therefore the product of two integral becomes double integral only if you use distinct variables. See, here I used lambda 1 and here I used lambda 2. So we used two variables, lambda 1 and lambda 2 here. You can ask why I am doing two variables and a double integral here instead of doing the same thing like product of two integrals. I am using double integral. Please note that double integral is quite different from product of two integrals. Okay, so suppose you have an expression like this, let's say x times, note, suppose x into dx 0 to 1 whole squared. So this is x squared by 2, the limit is 0 to 1 whole squared. This 1 by 2 whole square, it is 1 over 4. The same integration I can do as follows: x into dx 0 to 1 0 to 1 x into dx. So this is going to be x square by 2 0 to 1, and here also x square by 2 0 to 1. So 1 by 2 times 1 by 2, which is 4. Or this product of two integral, or this one I can write as double integral. The limit is same, 0 to 1 0 to 1, but here let me use two different variables. Okay, and it becomes double integral. See, this is a product of two integral and this one is double integral. Please recall the difference between product of two integrals and double integral, single integral, triple integral and multi-dimensional integral. So I am converting this one dimensional integral into two dimensional integral. x1 times dx1 and x2 times dx2. Okay, let's say this one is x1 and this one is x2. Now rearrange this: x1 equal to 0 to 1, integral of x2 equal to 0 to 1. Now x1 x2 dx2 dx1, first integrate with respect to x1. So 0 to 1 x1, this is x2 squared by 2 and the limit is 0 to 1 times dx1, and this is again 1 over 2. So 1 over 2 times x1 dx1. So 1 by 4, the same answer you can get it. Therefore product of two integrals can be written as a double integral provided that you used two distinctive variables, okay, in the double integral. Okay, so in this previous expression we used here we used two variables, lambda 1 and lambda 2 here. You can ask me why I am doing two variables, lambda 1 lambda 2 and double integral here, because I am going to find out in terms of the autocorrelation function. For autocorrelation function we need two time instants, so that is why we have chosen two time instants, lambda 1 and lambda 2. For autocorrelation function we need a two time instants. Okay, so we have chosen lambda 1 and lambda 2, two different time instants. Therefore I am going to find out in terms of the autocorrelation function. Excuse me. If you have used lambda 1 lambda 2 to be the same, then well, it does Well, it does not really bring the autocorrelation function into evidence, so you cannot get autocorrelation function. Now what I do is I play the usual trick, that is interchange the expectation and integration operators. If you look, the integration is here and here this operation and this operation, both you interchange. Once you do that, then it is equal to double integral of both from minus infinity to minus infinity expected value of x of t minus lambda 1 times x of t minus lambda 2, and h of lambda 1 and h of lambda 2 are constant, you can pull out from the expectation. D lambda 1, d lambda 2. Okay, now you notice that this is simply the autocorrelation function, ACF. So the expected value inside this double integral is simply the autocorrelation function of the input random process x of t. So it is the autocorrelation function of input random process RP, that is expected value of x of t minus lambda 1 times x of t minus lambda 2 is equal to what? The autocorrelation function or xx of t minus lambda 1 comma t minus lambda 2. Okay, now what is the time difference in this? T minus lambda 2 minus t minus lambda 1. So t will get cancelled. You will get a minus lambda 2 plus lambda 1, that is lambda 1 minus lambda 2. Therefore I can write or xx of lambda 1 minus lambda 2. Since the autocorrelation function is an even function, you can also write or xx of minus of the argument, that is lambda 2 minus lambda 1. Both are same. Either you can write this or this. Okay, now substitute this guy here. Not here, wait a minute. Yeah, here. Okay, so that is going to be double integral of or xx of lambda 2 minus lambda 1 times h of lambda 1, h of lambda 2, d lambda 1, d lambda 2. This is expectation of y square of t. Okay. Now this is the general relationship between the mean squared value and the autocorrelation function. Mean squared value of the output process y of t and autocorrelation function of the input process x of t. So this is a general relationship. So you must understand that x of t and y of t are two different processes. X of t is a different process, different random process, and y of t is a different random process. So what we are doing therefore is to express mean square value of one process in terms of the autocorrelation function of the other process. Okay, so that's what we are doing here. We are expressing the mean square value of the output process in terms of the autocorrelation function of the other process in terms of some other operation. Okay, so some other modification we are doing here. So the other process is going to transform in the LTI system, or going a transformation in the LTI system. That is, the input process is going a transformation in the LTI system, which is reflected in the product of h of lambda 1 and h of lambda 2. That means what? The input is x of t and its autocorrelation function is Rxx of lambda, I can say lambda 2 minus lambda 1, and this autocorrelation function is going a transformation in the system, in the LTI system. Okay, and that transformation is reflected in the form of like product of h of lambda 1 times h of lambda 2. That is evident from this expression. So it cannot be simplified further, unfortunately. Okay, so this expression is even you can simplify, but it is very difficult. Okay, so also, although this is usually not difficult or difficult to evaluate, since both Rxx of tau and h of t are likely to contain exponentials. See, whenever you find Rxx of tau or h of tau, these are all exponentials. Okay, likely to contain exponentials. Therefore, it is frequently very tedious to carry out the details. The reason is like it may contains infinite number of or many number of discontinuities. Like especially when lambda 1 equal to lambda 2, then there is a problem. Okay, so this is because such autocorrelation functions often have discontinuities or discontinuous derivatives at the origin. This guy has often have discontinuities, especially at origin. So therefore it is difficult to simplify further this expression. Simplify further because of the discontinuities in the autocorrelation function. At the moment, however, it is instructive to consider a much simpler situation, that is one in which the input is sample function input is a sample function. Okay, and this sample function comes from white noise. Okay, so let's say your input x of t is white noise. So you have many sample functions. Take any one sample function and give it as an input to the LTI system. Okay, and the output you denote it by y of t or the specific waveform y of t. So the input process is white noise process. It is white noise. If it is white noise, then the spectral density is equal to constant. Recall from the previous lecture, like when the noise is white noise, then the spectral density is constant. Spectral density is constant. That means Sxx of omega is equal to n0 by 2. Okay, so for white noise, spectral density Sxx of omega is equal to a constant, and this constant is n0 over 2. Therefore, if you take inverse Fourier transform, then you will get autocorrelation function, and that autocorrelation function is going to be n0 by 2 times del of t, or if you are talking about tau, then tau. Therefore, your mean square value of your output is going to be integral minus infinity to plus infinity, and this Rxx of tau is n0 by 2 times del of, instead of del of tau, it is lambda 2 minus lambda 1. Why it is lambda 2 minus lambda 1? Because here we had a Rxx of lambda 2 minus lambda 1, right? So therefore that is replaced by like this. Then h of lambda 1, h of lambda 2, d lambda 1, d lambda 2. Now I play the usual trick, bring this lambda 1 here, d lambda 1, let me do that integration at the last. Then in this n naught by 2 is constant, you can pull out of the integration. Then del of lambda 2 minus lambda 1, h of lambda 2, h of lambda 1, d lambda 2, d lambda 1. Now in this thing, maybe I can rearrange this. Lambda 2 is a variable. Okay, so the integral exists only for lambda 2 equal to lambda 1 because of the impulse function. Okay, recall from your signals and system that phi of t multiplied by del of t is equal to phi of 0. Similarly, phi of t multiplied by del of t minus t naught times dt equal to phi of t naught, right? And lambda 2 times del of lambda 2 minus lambda 1 d lambda 2, which is equal to phi of lambda 1. So instead of t, I can put t2 here. Instead of t naught, I put lambda 1. So therefore, this is going to be n naught over 2 integral d lambda 1. This integral will go away. That is going to be h of lambda 1. Already I have one more h of lambda 1 times d lambda 1. So n naught over 2 integral of, sorry, this anyway that will go away. I am sorry, this step will not, because I brought here. Let me rearrange this. H of lambda 1, h of lambda 1, d lambda 1. Okay, so n naught over 2 minus whole square times d lambda 1. This is the mean square value of the output process for a specific case. That specific case is white noise. Expected value of y square of t. So this means that the output mean square value is equal to the spectral density. By the way, n naught by 2 is the spectral density, right? Sxx of omega for white noise. Spectral density n naught by 2 multiplied by simply the area under the square of the impulse function. Okay, that is h square of t versus t if the input process is white noise. Therefore, and again this is constant, okay, for a given system, because you are doing the integration from minus infinity to plus infinity. Therefore, let me use y square bar for expectation of y square of t. This is equal to, the constant is n naught over 2 times area under the function h square of t versus t curve. So this is the mean square value of the output process. So till now we have looked at two things. One is mean value, that is in the previous lecture, mean value at the output of the, or mean value at the output process. Then second, we have seen the output mean squared value. or mean squared value at the output. So this one we denoted by y bar and this we denoted as y squared bar. So if you know the mean value and the mean squared value, you can of course find its variance, sigma y squared equal to y squared bar minus y bar whole squared. So this is the relation between the variance and the mean squared value and the mean of the output process. So at this point let me stop. Okay, in the next lecture I will come up with an example problem. Thank you very much.